Now let's look at this example. This is the typical example in the linear program. Okay, this example is the production scheduling. So a furniture shop makes tables and chairs. Suppose the tables each require 40 hours to build, and the chairs each take 30 hours to build. But the company can only pay for 1,200 labor hours per week. Also, suppose the table requires $80 in materials each, while the chairs only require $25 in material apiece. The company wants to limit spending on the materials to 1,700 per week. So the company does expect to sell all their tables and chairs to make a profit of $50 per table and the $20 per chair. Given this information, how many tables and how many chairs should the company plan to make each week to earn the most profit while staying within the constraints? So what are the constraints? The constraints as the first one is only pay for 1,200 labor hours and only pay for the materials to $1,700, right? So this is the constraint. So let's summarize using a table to help you to understand the problem because there are too many sentences, right? So now let's look at, we make a table to help you to understand, to summarize this problem. So this is the tables, and this is the column is the chairs. The first row is the labor hours. The table need 40 hours each, and the chairs need 30 hours each. And the company can only pay for 1,200 labor hours per week, so it should be the total labor hour should be less than equal to 1,200. And the second row represents the second constraint, which is the material spending. Materials. For each table, it will cost $80. For each chair, it will cost $25. So the company wants to limit spending on materials to 1,700. That means the total money should be less than equal to $1,700. Let's look at the profit. For each table, the profit is $50. For each chair, the profit for each chair is $20. And we want to maximize the profit. Okay, so if we let x be the number of tables it will produce every week, and y be the number of chairs. Okay, and we want to maximize. So now let's set up the linear program. Okay, set up the linear programming problem. So the first part, which is, so we introduced the two decision variables, x and y. X is the number of the table, and y is the number of the chairs. So we want to maximize, max, to denote the maximize The profit, we use Z. Z represents the profit. Z is equal to, what is the profit? Each table, the profit is $50. So X tables, you will have 50 times X dollars. Plus, the profit for a chair, each chair, the profit is $20. You have Y chairs, so it's 20 times the Y. So if you plus together, it would be the total profit, right? So we want to maximize this Z. Z represents the total profit. What is the constraint? Constraints. The constraint is followed by these two. The labor hours cannot exceed 1,200. So for the table, the labor hours is 40 times X because for each table costs 40 hours. And for the chair, the labor hour is 30 times Y. So 30 hours each chair, you have Y chairs. So the total labor hours cannot exceed 1,200. So that means it's less than equal to 1,200. This is the first constraint. The second constraint is the material spent, the money on the materials. Okay, so the tables, each table costs $80. So its total is 80 times X dollars. Plus, for the chair, which is 25, so it's 25 times Y dollars for chairs. It says it cannot exceed, they want to limit the spending on the materials, which is 1,700, so it should be less than equal to 1,700. Okay, these are the two constraints. But this is our real life problem, so we require that X, we also have another two constraint. X should be greater than equal to 0. And Y should be also greater than equal to 0 because these are the numbers of the tables and the numbers of the chair, the number of the chair, right? So it's always a non-negative number, so it's greater than equal to 0. Y is also greater than equal to 0. So now, this next part, we want to use the geometric approach to solve this linear programming problem. So this is called the linear programming problem. Okay? So we need a tool for the geometric approach. We know we need to find the feasible region, right? How can we find the feasible region? We notice that these are the system of linear inequalities. We can use these constraints to find the feasible region. So in other words, X, Y should satisfy these four inequalities, right? So now let's look at what is the feasible region. Let's draw the graph. $20, $40. This is 20, 40, 60. So now let's look at the first one, which is, we use another color. 40x plus 30y equals 1,200. Okay, so we need to draw the boundary first, right? So we have 2 points. We need to find 2 points. 1 point, if x equals 0, y would be 40. If y equals 0, x should be 30. Right, this is the, so 0, 40 is here. and this would be the 30, 0. So you connect these two. So this is the line, okay? Which part? You just test 0, 0. If you plug in 0, 0, 0 times 40 equals 0 plus 30 times 0. So 40 times 0 plus 30 times 0, which equals 0, less than equal to 1000. Okay, so that means this is correct. So the region less than equal to 1200, which is this part below this half plane, okay, below this line. And the line is included because this is the equal sign, have the equal sign. Okay, so now let's look at the second one, which is, we use another color, blue color. 80x plus 25y equals 1700. Okay, so we have the points that if x equals 0, y equals 25y equals 1700, so you plug in, you will get y equals 68. If y equals 0, then x would be 21.25. 21.25 is here, for example. It should be very close, for example, is here. And 68 is here, for example. So if you connect these two, and which plane? Okay, it's divided into two planes. Which half plane? We still test the 0, 0 for our convenience. So 8 times 0 plus 25 times 0 is equal to 0, which is less than equal to 1700. Yes, it satisfies this inequality. So it should be the region below this line. Okay, so now we also have another one, which is x greater than equal to 0 and y greater than equal to 0. X greater than equal to 0 and y greater than equal to 0, it should be in the first quadrant, in this part, right? X greater than equal to 0, y equal to greater than equal to 0. So it should be in this region, right? X greater than equal to 0, that means it's on the right side of y-axis. Y greater than equal to 0, that means above x-axis, so it should be in the first xy axis divide our plane into 4 parts. This is the first part, right? This part. So the common part would be the purple region. This is the boundary of the purple region. Okay, so there is an intersection point. Okay, then this point is, we have some corner points, right? This is the origin, is 0, 0. And this point should be 0, 40. And this point is 21.25, 0. And this point, how is this point? This point is the blue line, the intersection of the blue line and the red line, right? The blue line is 80x plus 25y equals 1700, and the red line is 40x plus 30y equals 1200. Okay, if you solve this linear equation, system of equation, you will get x equals 15 and y equals 20, right? We can use the way we multiply the second equation by 2, right? Then subtract from the first equation. Oh, by negative 2, then add it to the first equation. You will eliminate x, right? We can use the elimination method. Okay, so you have this one, so this means it's 15, 20. Okay. So now, the next thing is we want to know which one gives you, this is a closed region, so the maximum profit always exists, right? So this one is the, we want to know where is the maximum, which one gives you the maximum profit. Here, or here, or here, right? It depends at each corner, so we need to test the values at each corner. So we have 0, 0, this is the 1 corner. We have 21.250. This is another one. We have 15, 20. We have 0, 40. Okay? So this is the z values. What is z values? So this is z equals 50 times 0 plus 20 times 0, which is equal to 0. This is the 50 times 21.25 plus 20 times 0, which is equal to if you use a calculator, it will give you 1062.5. This one, this is 50 times 15 plus 20 times 20, which is 1150. And this point gives you that 50 times 0 plus 20 times 40, which is 800. So that means if the company produce 15 tables and 20, so 15 tables and 20 chairs give the maximum profit, which is $1,150. Okay, so this is the result for this problem. Okay, so you see the linear programming is very complicated. So the first thing you need to set up the linear programming correctly. It contains two parts. The first part is to maximize or to minimize the objective function. It's from the problem, the question of the problem, right? It asks you to do what, which is the objective function. Then you need to use the conditions in the problem to get the constraints, right? So after you set up the linear programming problem, then you need to use the constraint to find the feasible region. This is called a feasible region. We use the way to find the solution region for a system of linear inequalities, okay, which we have learned in the previous section. If you are not familiar with that, you can go back to check that section. After you find this feasible region, then you need to locate the corners, because as we said at the beginning, that it only happens at the corner. So we need to find all the corners. Then we use a table to calculate the z values or the objective function values at each corner. Then the maximum value, if this problem asks you the maximum profit, so here, then this one is the maximum. This one is the maximum, right? It will give you that 15 tables and 20 chairs makes the maximum profit, which is $1,150.